Hello, my name is Penina Levine, and I am a master's student at MIT, working in nuclear security to make our arms control treaties more secure. Specifically, I'm doing this using a method called neutron resonance transmission analysis, or NRTA. NRTA uses resonant neutron absorption that is unique to individual nuclei to identify isotopic compositions of a target object, for example, special nuclear materials. So this is useful for warhead verification in arms control treaties, as well as for fresh and spent fuel enrichment analysis. However, a limitation is that NRTA is currently carried out at very large, expensive facilities. So I'm looking at a method to a setup to make NRTA smaller, simpler, and mobile. Specifically, I'm doing this using an isotopic source and detection in 2 different detectors. So right now I'm doing simulations with the hope that in the future I will move to experiments very soon. Right now I'm using Grasshopper, which is a JAUNT4 backed Monte Carlo simulator. And I'm using an isotopic source, as I mentioned. So this can be PUBY or AMBI. And right now I'm using AMBI with a source rate of 10 to the 4 neutrons per second. I'm also using 2 detectors. So if we see in this geometry here, we have our source, which is AMBI, and a neutron comes off of that source, interacts in detector 1, is moderated in detector 1, and then hits detector 2. And so I'm looking at coincident events. When we record a hit in detector 2, we open up our time of flight window and then find our coincident events in detector 1. And that allows us to reproduce our energy of the neutrons from time of flight. However, as I've mentioned, we do have moderation in detector 1. And while that's important for this system, it is the limiting factor on our energy resolution because there's some randomness associated with how long it's going to take that neutron after it's been detected in detector 1 to actually make it out of that detector. So here, we actually see, this is a log plot on the left, and we can see that with our moderation resolution increases, it improves with an increasing neutron energy. So that's unique to this system, that our resolution gets better as our incoming neutron energy increases. So that's great, but now the next question is, we have our time of flight reconstruction. How well is that accurately reproducing the true neutron energy? And that's what this plot here shows. On this blue line, we see the 1-to-1 ratio, where that would mean that we're perfectly reproducing our energy. We can see that our time of flight runs a little bit high in comparison to our true neutron energy, but we're really close to that line, which is reassuring, and we can always fix this a bit later with data processing. Our main concern is that our signal to noise ratio is quite low. We're looking at 6. And that's because we're having a lot of high energy neutrons that are somewhere above this plot that we can't distinguish between in experiments. So in the future, that's our main goal, is to bring that down. And I'll discuss some strategies that I'll be trying next to figure that out. However, we can go ahead and look and see how this method would do for real NRTA. And we can do that by looking at our neutron spectrum, the energy spectrum. And so what this is our open beam and our attenuated beam through a silver foil. And we can clearly see this resonance here, where neutrons are being absorbed at around 5 eV. And that corresponds to our silver resonance, which is how we can identify what this is. Overall, this really shows that we have the potential for compact mobile NRTA experiments with improved energy resolution. And this is really important. This will help the DOE to better understand fresh and spent fuel enrichment analysis, and as well to verify arms control treaties. So as I mentioned, some of our limitations right now are just the signal to noise ratio, which I'll be looking at reducing by looking into incident angles to see if there's somewhere in our geometry where we're getting some kind of scattering or moderation that we're not accounting for. As well as I'll also be looking at ways that we can look at an arbitrary time of flight window to subtract background that we might be seeing as a kind of way of data processing. But overall, this is a really promising method to achieve smaller, simpler, and mobile NRTA. Thank you.